So to complete 7b, part 2, we'll talk about the probability of an event happening at least once. So this is a complementary situation. So the complement of something happening at least once, an event happening at least once, as complement, the event does not happen. So those are exactly opposite, and they make up the entire realm of possibility. It either happens at least once, or it never happens. So we're able to use our complement rule. So the probability of an event happening at least once is equal to 1 minus the probability of that event never happening. This is a pretty powerful rule, and it's one of the most complicated ones we'll use in this chapter, but it's worth learning. So the probability that a region prone to flooding will flood in any single year is 1/12. 1 out of 12. And just assume from year to year that's independent. Any given year, the probability that this region floods is 1/12. So what is the probability of a flood occurring 3 years in a row? Okay, so we're going to answer 3 questions by the time we're done with this page and this example. And it's really just working up to question 3 down here. What is the probability of a flood occurring at least once in the next 3 years? This is probably one of the most practical questions that this example asks. So in 3 years, how likely is it to flood or not? So to get there, part 1 and part 2 will guide us. So part 1 again asks, what's the probability of a flood occurring 3 years in a row? So what is the probability that a flood occurs 3 years in a row? So that is the probability of a flood the first year. Here's where we hear the word we need to hear, and a flood the second year, and a flood the third year. So flood, and flood, and flood. Okay, we know with an and probability, or and events, that we can multiply. It's from our and rule. Probability of a flood times the probability of a flood times the probability of a flood. Okay, well, each year is independent, so those probabilities are independent, and we can multiply 1/12 times 1/12 times 1/12. And 1/12 cubed. Of course, the calculator can handle that, and I'll leave that to the student to work out. Now, the next part of this example, part 2, what is the probability that a flood occurs, what is the probability of no flood occurring for 3 consecutive years? No flood occurring for 3 consecutive years is the probability of no flood and no flood. Again, same situation. Each year it cannot flood to satisfy this event entirely. And we know that this is really 3 events linked together. Not flooding for 3 consecutive years is no flood and no flood and no flood. So again, it's an and, the probability of no flood. And there's going to be 3 of them, so we'll just cube the probability of no flood. Well, if the probability of a flood is 1/12, the probability of no flood is the complement of a flood, so 1 minus the probability of a flood. Okay, so that is 1 minus 1/12. Common denominator of 12/12 for 1, and we have 11/12 is the probability of no flood. Okay, so this is equal to 11/12 cubed. And I'll let the reader fill those in too. Whatever that value comes out to, 11 cubed over 12 cubed. So now we're getting closer and closer to our final question. Got all the tools we're going to need for it. Question 3 asks, what's the probability of a flood occurring at least once in the next 3 years? Okay, at least once in the next 3 years. So probability of at least one flood in 3 years. Okay, Our complement rule says that this is equal to 1 minus the probability of no flood in 3 years. Well, that's really convenient because part 2, question 2, gives us that answer. No flood in 3 years is 11 over 12 cubed. So this is 1 minus 11 over 12 cubed. So just to get those values for students, and so we can see, check our final answer here. 11 over 12 cubed is 11 cubed. So back to the top. It's 1,331 divided by 12 cubed, which is 1,728. So our final answer as a fraction will look like this. 1,728, just to give the details. That's 1331. We have 397 over 1,728. That's what we should get ultimately. Probability of no flood in 3 years. So now the reason this rule is handy is you might imagine that in order to satisfy the at least once criteria, right here, this could be really difficult. That could be 1 flood in the 3 years. It could be the first, second, or third years. We have to account for all of those arrangements. It could be 2 floods in 3 years. First 2, last 2, outside 2, middle 2, or 1 or 3, 1 flood for each of the 3 years. So 3 floods in a row. So at least once really helps us to take care of a whole batch of things with just one simple calculation using that complement rule. It's a really powerful tool, and it gets us pretty far along in the next problem as well. So we'll do one more at least once probability problem. And this is kind of a famous birthday problem. So we suppose that 5 people are sharing a table in a classroom, all wearing masks. What's the probability that at least 2 people have a birthday in common? And we'll assume that nobody at the table has a leap day birthday. Okay, so let's go to this. Now, probability that at least 2 people of 5 have a common birthday. It's a lot to write. Well, again, we could start to look down the long path of this problem. 2 people could have a birthday in common. It could be the first person, the second person. It could be the first and the third person. It could be the first and the fifth person. 3 people could have a common birthday, and that could be any combination of them as well. So there are a lot of outcomes and a lot of events to link together and try to track down if we're going to do this a direct way. But our formula for at least once using the complement is fantastic. The complement of at least 2 people or at least 1 pair of common birthdays occurs at this table is 1 minus the probability that no common birthday, there is no common birthday in 5 people or among 5 people. Okay. So the complement of at least 2 people having a common birthday, or there being at least 1 common birthday in the group, is equal to 1 minus the probability that there are no common birthdays in the group. So we can take apart this line here as an and. It means the first person has no birthday in common with anybody else. The second person has no birthday in common with anybody else. The third person has no birthday in common with anybody else, and so on. And we're hearing an and in that, so we know that we'll multiply. So this is 1 minus So the first person has 365 possible days out of the 365 possible days that their birthday could occur on, because no other birthdays are, in a sense, taken at this point. So this is the first person. Okay. If we stopped here, this would be the calculation for what's the probability that one person has a birthday in common with somebody else, or with somebody else at this table, when there's only one person at this table. So if there's only one person at the table, the probability of them having a birthday in common with another person is 0. So this answer makes sense. This value right now makes sense as is. Now for the second person, I'll make a note here for the first person, has 365 possibilities. Now we know that with each of these and steps, the next person does not have a birthday in common with the person that we've already checked or that we've already written down. So the second person has 364 possible birthdays divided by 365. Okay, so this is, I'll just write second person below. And we continue down the line. The third person, 363 over 365. Because 2 birthdays are already taken, so they're left with 363 possibilities. The fourth person, 362 over 365. And we end at the fifth person. 4 birthdays have been taken. They have 361 left out of the 365. Now this is equal to, one quick way to sketch it is 1 minus 365, 364, counting down. And I'd encourage students to check this in their calculator to make sure they can come up with the correct decimal. Sometimes that's not always trivial. Divided by 365 to the 5th power. Simplify things here. Let's get that fraction on the right as a number, or a decimal. And we have, counting them down, and dividing by 365 to the 5th. This ends up, we're at approximately 1 minus 0.972, round that to 9. It was 86, so we'll round to 9. And as this one, we end up with 0.0271. So it's a fairly small possibility, but it's about 2.7%. So that's what our rounded answer would come out to 4 decimal places. If we wanted to think of it as a percent here, we can put it down as at 2.71%. Not a very likely chance, but of course, as the number of people go up, that probability will increase. So that's it for at least once probabilities. This is one of the hardest problems we're really ever going to do in here in terms of thinking our way through something. But practice some of the ones in the book, and good luck.